let's talk about something that I called graphs from the Hall of Fame in the notes. I called them this because my favorite professor of all time called them this in his lecture notes. I just think it was such a cool thing. So I want to talk about the following question here. So we're still talking about colorings. And the question kind of is like, what causes the chromatic number to be the chromatic number? We have an upper bound now. We know that the maximum degree is an upper bound, or certainly maximum degree plus 1 is always a safe upper bound. And we had some like baby lower bounds, like the clique number, right? If you have a complete graph of size 10, then your chromatic number is definitely at least 10. Also, n divided by alpha was also related to it as well. You'd need a certain number of colors because of the size of color classes and stuff. But like, that's one way to force your chromatic number up, is have a big clique inside the graph. But it turns out you don't need that at all. You can have very high chromatic number and have no triangles in your graph, for instance. If you have no triangle, it means you have no complete graph whatsoever, right? It means like if you look at 3 vertices, you'll never see 3 edges, right? Because that would be a triangle. Even with that, you can have chromatic number as high as you want. And so that's kind of what the first thing I want to start with today is construct graphs that have high chromatic number as high as you want, but don't have triangles in them as the first step for showing, okay, it's not having a bunch of triangles that forces you to have high chromatic number. And remember this relationship with bipartite graphs, right? Bipartite graphs have chromatic number 2, and they have no triangles, and they have no odd cycles whatsoever. So like you need odd cycles certainly to push your chromatic number up, because without odd cycles you have chromatic number 2, but it doesn't have to be triangles. It could be long odd cycles, in fact, and we'll see. We'll flesh this idea out further. But so what we want to do today is, so in sort of answering this question, I mean, so the answer to the question, what forces up the chromatic number, is we don't know. Like it's not well understood. Like it can be really high despite other properties of a graph being unexpected. So what I want to rule out is it's not the abundance of triangles, basically, okay? And in fact, we'll find out later, it's not the abundance of short cycles at all. You can have an absence of short cycles entirely and have very high chromatic number still somehow. Okay, so let's just, we're going to construct what I'll call triangle-free graphs. So triangle-free means it has no triangle subgraph. With high chromatic number, okay, with high chi. Chi is the chromatic number of the graph. And by high, I just mean I'll show that they exist with every chromatic number available. Okay. It's not enough to just produce one of chromatic number 10 with no triangles. I want to show it's possible no matter what chi is. Okay. All right, and so all of these constructions are somehow recursive, and they all each have a special name. The first is the McCleskey graph. So given G, the McCleskey, how do you spell this? McCleskey graph, M of G, so of G. So we're going to take a graph and we're going to modify it somehow to get the McCleskey graph, is constructed by adding a vertex V prime for each V in the vertex set of the original graph. So you duplicate every vertex, and that new vertex V is adjacent to the neighbors of V. So each vertex you copy and join it to the neighbors of that other vertex. So it looks identical to the original vertex. It's not adjacent to V itself, though. I mean, you don't need to put that. If I don't say that it's adjacent, it's not adjacent, but it's worth emphasizing here that I don't make it adjacent to V. And then I add one more vertex and another vertex Z joined to all new vertices that look like V prime. Okay, so let's do a couple examples here. So if I give a graph, I'm going to add one vertex for every existing vertex, join it up to this, basically copy each vertex. And then I'm going to add an additional vertex Z that's joined to all these new vertices. Okay, so say my graph G is like just a very simple path here, right? So this is G. Then M of G looks as follows. We copy these three vertices and we duplicate their adjacencies. So this vertex is a copy of this vertex, so it's adjacent to the middle one, right? It's copying that edge there. This one here is adjacent to that one. I mean, it's copying that one, so it's adjacent to this and this. And then this one here is adjacent to the middle as well, right? Copying that edge. And then I add a new vertex Z that's just adjacent to these three. Okay, so that's M of G for the path G. Let's do it again for the 5 cycle because it's pretty. So usually we kind of draw it in this way, that this is the, this is the G, this is the copy of G. It's not a copy of G, it's a copy of the vertices of G, and then Z. But when I do the C5 here, the 5 cycle, it's a little bit nicer to do it in the following way. So let's duplicate all these vertices around the cycle and just draw them again in a cycle. And then there's going to be an extra vertex Z in the middle here. Okay, now Z is adjacent to all the new vertices. So it just looks like this. And then remember, the blue vertices aren't a copy of the graph itself. They're copies of the individual vertices. So this blue vertex here is a copy of this one. So it sees the same neighbors. So it goes here and here. And this one is the same as that. So it goes up here and down here, over here and over here, there and there, and then finally there and there. Okay, so this is M of the C5. C5 is how we denote the 5 cycle. Okay, so you get that nice graph there. Okay, so once you, I mean, it's easy to construct them by the rules. Coming up with like what's a pretty drawing afterwards is like, that's not easy, but that's a whole different question. In fact, actually, that is a very interesting and difficult question, and a topic in graph theory is what's called graph drawing. It's closely related to planar graphs, but the question of like how to draw them in some kind of nice way. You have to define what nice means, of course. Yeah, anyway. So there's a certain art to it as well. Okay, so just if you notice in like this example here, this McCleskey graph here, it's still triangle free. It started out triangle free, right? The C5 has no triangle, and if you examine it, there's no triangle in it. And if you look carefully and think about it a little bit, the 5 cycle had chromatic number 3, right? And this new graph will have chromatic number 4. It has to go up somehow based on the construction. Okay, that's not immediately obvious, but that will be the theorem. Okay, so the theorem is that if G is triangle free and G has chromatic number K, then the McCleskey graph of G is also triangle free, and its chromatic number, so chi of M of G, increases by 1. Okay. The proof of this is going to be an exercise. This will be on the next homework set. Okay. An induction is probably a good idea here. Okay. Basically, you use the fact that G is triangle free and has chromatic number K to show that the next one has to go up. Can't stay the same is maybe a better approach. Okay. But what does this theorem tell us? This theorem tells us that if I start with a graph, the C5 is usually the place we start. That's triangle free and has chromatic number, triangle free and has chromatic number 3. And M of G of this graph will be triangle free and have chromatic number 4. And M of G of that graph will have chromatic number 5. And M of G of that will have chromatic number 6. So you can just keep doing this operation forever and get whatever chromatic number you want and never introduce a triangle when you repeatedly apply it here. So this proves the existence of graphs without triangles and with arbitrarily high chromatic number. And typically, like if you look up in the literature on Wikipedia, the McCleskey graph often is only defined to be the C5 and the iterations on it. But we gave a slightly more general definition where I can start with any graph I want and do this operation to it. But typically, in fact, sometimes you'll even see that like M of 1 is actually the single vertex, and then M of 2 will be, you take a copy of that vertex, join it to its neighbors, so nothing happens, it has no neighbors, and then add a vertex Z that's adjacent to both of them there. And then M3 will end up being this graph here, because I take That's not right. That's not right. What did I do wrong? Okay, maybe M1 is a single edge. Yeah, that's how it is. I did it wrong. You don't start with a single vertex. If M1, again, you can do this for any graph, but if M1 is a single edge, then M2 ends up being the C5. Here's my single edge. And then these guys are swapped, but this is a copy of that vertex. This is a copy of that vertex. So the adjacencies are correct. And then this is the new vertex joined to both of those guys there. So this would be M2. So the C5 is M of the single edge. And then this is M3 up here, right, that we created already. And you continue this on forever. Okay. So that one I'm not going to prove, but I'm going to tell you two other constructions and prove that those ones are triangle free and so on. Okay, so the next, and these ones are a little more complicated. The McCleskey's the easiest, I think, to understand. Okay, so the next one is the Zykov graph. ZK, or I will define ZK plus 1, is defined as follows. So Z1 is a single vertex. Okay, so not in McCleskey starts with an edge, Zykov starts with a single vertex. And my goal again here will be to create a triangle-free graph whose chromatic number is larger and larger and larger. Okay. Okay, so how do I create ZK plus 1 from ZK? So ZK plus 1 is K copies of ZK, so the previously constructed graph, and a set AK of lots of vertices of V of Z of K to the K vertices. Okay, so I take K copies of the graph ZK itself. I don't know what that looks like. At first, it's just K individual vertices. And then I take the number of vertices in a copy raised to the K, many additional vertices in AK. And actually what I'll say here is the set AK, these are vertices, but is set of tuples V1, V2, VK, where VI is in, so VI is a vertex of the ith ZK, a vertex in ith copy of ZK. Okay, so AK are a set of vertices, but you can think of those vertices as literal tuples, right? We do this when we think about the hypercube. The vertex set of the hypercube are literally the strings. Like vertices can be any object you want. It's actually very handy to think of graphs in this way sometimes. It's not vertices as being some special object, but of being actual things you're talking about. They could be like subgroups of a group, and you could join them together for, following certain properties and things like that. So the vertices of AK literally are tuples of vertices. Okay, so it's a tuple, it's of vertices. And what do? I join the vertex V1, VK, that's just to emphasize, in the vertex set of AK. Well, AK is a set of vertices, so in AK, to vertices, the vertices themselves, V1, V2, up to VK. Each of those is in a copy of ZK. Okay, I'll draw a picture here in a moment. So what goes on here is that for every tuple that I can choose a single vertex from each of the copies, that I create a special vertex corresponding exactly to those guys that'll be joined to them. Okay, so let's look at a picture here, how this graph looks. So say I've got ZK, then I take K copies of ZK. So here's ZK, 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 ZK. And then I introduce this huge set of vertices here. And here, how do I get, what's a vertex? I choose any set of vertices, one from each of these classes here. And for that collection, I introduce a unique vertex up top that they'll be joined to. Okay, so this vertex here is V1, V2, VK. That's like the pattern that it's adjacent to. Okay, hold on. Martzi. Okay, does this construction make sense? So I introduce a bunch of new vertices, one for each way of choosing one vertex from each of these K classes that I dropped down here, right? And so that's why the size of this is V, ZK raised to the K. That's the number of ways to pick one vertex from each of these classes. ZK times ZK times ZK dot 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 times ZK. For every way of picking those vertices, you have their pattern up here, and then you make the sort of natural adjacencies. Okay. Okay, so the theorem is that this graph theorem ZK plus 1 is triangle free, and the chromatic number of ZK plus 1 is K plus 1. Okay, so the proof, this one will prove, is by induction on K, no surprise here. Okay, so when K equals 0, we're examining Z1, which is just the single vertex, which is definitely triangle free, and its chromatic number is 1, which is K plus 1 in this case. 0 plus 1 is 1. Okay, so base case holds. Kind of boring. Okay, so now we're going to assume that ZK is triangle free and has chromatic number K. That's the inductive hypothesis. And the first thing we're going to do is first show that ZK plus 1 is triangle free. Okay. All right, so how does this go? Let's look at our construction real quick here. Actually, we can prove it by looking at the construction. What does a triangle look like? Okay, there's no triangle inside of a ZK, right? Because ZK is triangle free by induction. There's no edges between two copies of ZK. I didn't say anything about that. And there are no edges up here either. This big set up here is independent. Okay. So a triangle can only look like a single vertex from up here and then two vertices from down below. But those two vertices can't be in different classes. They've got to be in the same class. So this vertex would have to be joined to this one, and then there'd have to be an edge here. But does this happen in my construction? No, each vertex above is joined to only one vertex per ZK. Namely, it's joined to V2 in the second graph. It's joined to V7 in the seventh graph, and so on. So each of these sends one edge to each class. So there's no triangle. I don't get a triangle even if by the fact that there wasn't one in the first place, right? So there's none in the ZK, and you can't create a cross triangle here because of the construction. Okay, so we'll just go with that. So ZK is triangle free. I mean, we proved it by examining the picture there rather than writing it out. Okay, and now show that the chromatic number goes up. Equals K plus 1. Okay, and actually here I want to show two things. First of all, I want to show that the chromatic number is at least K plus 1 and it's at most K plus 1. I want to be precise here. I don't want to show that it's just at least K plus 1. I want to actually get each one because maybe it jumps up by 10 or something like that. Okay, so first let's actually confirm that the new graph has chromatic number K plus 1. And let me just redraw a picture here. Okay, so here's my new set AK plus 1. Oh, by the way, when I define this up here, maybe I called it AK accidentally. Yeah, typically we call the new set, it should share the index of the graph we're creating. So AK plus 1, AK plus 1, right? AK plus 1 is the new set of vertices in ZK plus 1. Doesn't change anything, just the name there. Okay, so we redraw the picture. Here's your copies of ZK. And then I have edges going up the top here. Can anybody see why I can color this with K plus 1 colors? So K plus 1 colorable, I'm asking. Why is this graph K plus 1 colorable? It might be K colorable. We'll deal with that in a second.
Every element of A the same color?
Yeah, exactly, Ethan, right? A is a huge independent set. So if I color all these with the same color, I lose one of my K plus 1 colors. But these things down here, they only take K colors by induction. And they send no edges between each other. So just color each of these with K colors in the identical way as given by induction, and then introduce or use the K plus first color for the vertices up here. then I'll have no adjacencies. Okay, super easy, right? So use new color here. Okay, so certainly this means that the chromatic number is at most k+1, right? I just produced a coloring with k+1, but the question is, do I need an additional color? Maybe I don't actually need to introduce a new color. Okay. So can I do better? Okay. In other words, I'm asking the question if the chromatic number of zk+1 is, well, let's say is at most k. I want to rule this out. I want to say that I can't use k colors. Okay. Okay. So suppose I can get away with using k colors. Then, yes. Okay. Then here's what I want to do. Is it what do I want to do? What colors these are? Yes. Okay. So if I can get away with k colors on the entire graph, then all k colors appear in each of the copies of zk. Because by induction, the chromatic number of these smaller graphs require k colors. So these use all k colors, right? In the previous example, there might be other colors where I don't, colorings with k+1 where I don't use, obviously these don't have to use all k+1, right? But now I'm stuck with only k colors. So all of them have to appear in each of these blobs here. Every single color appears in those. Okay, and so then what I'm going to do is pick a vertex vi from ith copy of zk with let's say that is colored with color I. Okay, so this graph, this zk sees every single color. Pick a vertex in it of color 1. The second copy sees every color, so pick a vertex in it of color 2. The third copy sees every color, pick a color of color 3. And the last graph sees every color, so pick a vertex of color k. Okay, and say those as before, this is vertex v1, that's v2, and this is vk. Now, for any pattern of vertices below, there's a unique vertex above that's adjacent to exactly that collection, right? So look at the vertex above v1, v2, vk. Remember, that's a tuple in ak+1. Look at the very specific vertex above corresponding to those vertices that I chose. Well, it's adjacent to a vertex of color 1, and a vertex of color 2, and a vertex of color 3, and a vertex of color k. So what color can I put on that vertex? I can't. I've got k colors, and it sees all k colors on its neighbors. So there's no color for that one there. So if I use k colors, well, I can't, is what it means. I get a contradiction, right? The whatever color I put on this vertex, I get an edge whose end vertices are the same color, okay? So this relied on me having k copies of zk here, and it also relied on me having a corresponding vertex up here for every pattern, right, of vertices down below, because I didn't know which vertex was, color 1, which was color 2, and which was color k. Maybe there was only one vertex of each of those in my coloring somehow, okay? All right, so look at that. It can't be properly colored, okay, which is a contradiction, okay? So the chromatic number of zk+1 is not less than or equal to k, it's greater than or equal to k, but we already showed it's at most k by producing a coloring, so the chromatic number of the Zkov graph for k+1 is k+1, okay? So the chromatic number goes up at each step, so keep duplicating. All right, now Zkov and McCleskey are sort of the two classic triangle free examples here. They have their advantages and disadvantages. McCleskey is smaller, fewer vertices are introduced, right? This takes k copies of the graph and then adds this huge set of vertices. So it's growing in terms of number of vertices much faster. McCleskey says just duplicate the existing vertices and add one more bonus vertex, okay? But these two operations for building a graph from another one are valuable in other contexts. Sometimes this one's better than the previous. They're tools for constructing one graph from another and inheriting, in this case, a triangle-free property, but there are other ways to do this as well. Okay, let me give another example. This is the Blanche-Descartes graph. We'll call it DK. Okay. This Blanche-Descartes is a pseudonym for generally for Tut, who we've seen in Tut's theorem. Tut was such a good mathematician that he published results under a fake name occasionally, just because he could. So, also he came up with this very like Blanche-Descartes, carte blanche, right? It's rather amusing. So anyway, so this graph has a nice history. Yeah. So there's a few other instances of people using pseudonyms in mathematics. There was actually a group that published under the name, oh, I can't remember now. Anyway, but someone know that one was going to say? Yeah, Bourbaki, thanks. That's one, Van. Yeah, Bourbaki's a group. There's a couple others. I know a currently working mathematician that also publishes papers under his daughter's names sometimes as well. So yeah, it's a nice privilege to be able to do this thing though, right? Generally, you know, when you publish new work, you want your own name on it. But anyhow, so let's look at the Blanche-Descartes graph. It's even better than the ones above here, as you'll see in a moment here. Okay, so Blanche-Descartes is also defined recursively, and we start off with D2, which is the 6th cycle. And D3 is the 7th cycle. Okay, so these are our two base cases here. We only need D3 for defining it. D2 just so that we can have, well, you'll see here. We can have every chromatic number that we want, right? So what's our theorem going to be? No triangle and has chromatic number k. So D2 has chromatic number 2. It's an even cycle. Obviously, it doesn't have a triangle. D3 has chromatic number 3 because it's an odd cycle. Also, obviously, doesn't contain a triangle. But for the definition, we only need this for the recursion. Okay. So DK. So k is at least 4. So we'll define dk in the previous we did zk plus 1, but it doesn't matter. Is defined as follows. All right, this one's a little bit trickier, but it's still not that bad. So we're going to start off with a huge set of vertices, similar to similar to AK. This serves a similar role. Okay, so let R be a set of, let me get the number right here. I think the number in the notes is wrong, but this is going to be a set of k minus 1 times d k minus 1. So we're going to basically think of this as k minus 1 copies of v dk minus 1, but just as that many vertices, and then plus 1. Okay, so we take a set of this many vertices, just call them set R. This value has a very specific reason for being chosen. It's going to get the pigeonhole principle to kick in, right? Like you have the product of these two numbers plus 1. It's going to be 1 more than like the number of bins. Some will overflow. Okay, so that's the reason for this number being chosen. Okay, and so now I've got R. So it's just a set of vertices. And now in Zkov's construction, what I did was each vertex up here had a unique pattern of individual vertices below that it was joined to. Here, instead of naming each vertex, I'm going to create a graph for every subset of vertices here. Okay, so it's like somehow it's more compact. Okay, so what I do here, this is R for each subset X of R of exactly dk minus 1 vertices. Whoops, dk minus 1 vertices. Okay, but I'm gonna have to draw this picture again in a second, but I grab a set X there, and how many vertices do I want to take at a time? As many vertices as are in the previously constructed dk minus 1 graph. Okay, so for each of those, I'm going to add a new vertex disjoint copy of dk minus 1. Okay, so for each subset of the set of vertices, I'm introducing a new copy of dk minus 1. So this graph's going to be immense, right? And I'm gonna name these as well, called or denoted, just so I can distinguish them from each other. So dk minus 1, the one associated with subset x here, I'll just put an x superscript there, just to keep track of it. Okay, and put any perfect matching between x and dk minus 1 to the x. Okay, so let's try to look at a picture here. This one's hard to draw, but this is the construction. So I've got R, and for each set x, I create a copy. I introduce a dk minus 1 to the x copy. Okay, and then I join these by edges. You can just choose a perfect matching. There's as many vertices in x as there is in dk minus 1, so I can pick a matching here. Okay, I don't introduce any edges into R. R will be independent, like in the Zkov construction. But what's different from the Zkov construction is, okay, so if over here I pick another, a different x, then I get another dk minus 1 here. Maybe let's call this one here y, just because. Right, so this is set y of the same size. I also put a matching in between this one here. But where this construction gets interesting, in some sense, is say I take a different set here, x prime, right, that intersects this set here. Now, I introduce a totally different dk minus 1 for that. These don't share vertices despite the fact that these share vertices, okay? That's what this was, a new vertex disjoint copy of dk minus 1. So this is dk minus 1 to the x prime. But when I join these things by a matching, like there's going to be some overlap, right? Like this, well, I didn't draw this very well, but this, this red edge goes into there, and there'll be a blue one going here as well. So this vertex above here gets like, its degree increases. In fact, you can predict the degree of a vertex here. It'll be how many times can a vertex be in a set X of size of the number of vertices of dk minus 1. Like you can compute that number if you want, but it doesn't matter. Okay. All right, does this construction make sense? For every single subset in R of the appropriate size, introduce a unique copy. Oh, this one should have a superscript of dk minus 1 corresponding to that, and just join them one edge to one vertex to one vertex. Okay. All right. So now the theorem for this is that dk has chromatic number k and no cycles of length 3, 4, or 5. So it's triangle free, but it's even better, right? There's no cycles of length 3, 4, or 5. In the Zkov graph and the McCleskey graph, we got short cycles. We did get 4 cycles and we did get 5 cycles. But this is even better. So let me explain why this is better and more interesting in some sense. So in Zkov and McCleskey, if you look locally at 3 vertices, you'll only see 2 edges, right? In the Descartes graph, if I grab 5 vertices, how many edges can I see on 5 vertices? There's no cycle on 5 or 4 or 3 vertices. So if I investigate 5 vertices at a time, I don't have any cycles, right? So on any 5 vertices, at best, I'm a tree. That's the densest I can be in terms of number of edges. So on any 5 vertices, you can have at most 4 edges. As soon as you have 5 edges on 5 vertices, you're definitely getting a cycle of length 3, 4, or 5, right? So locally, like again, on any 5 vertices, I don't see any reason my chromatic number should be high, right? Tree has chromatic number 2, by the way. I think we have proved that at some point. We haven't proved that. We proved a tree is bipartite, which means that it has chromatic number 2. So trees have low chromatic number. So locally, this graph has low chromatic number, but globally it has as high chromatic number as we want, okay? So we have plenty of time to prove this. So let's go through it. And the proof's actually not that hard, despite the fact that the construction is a little bit complicated, okay? So I'm gonna redraw the picture here. Let's examine cycles first, okay? So let's just say cycles. Let's figure out what a cycle looks like in this graph here. Okay, so we've got R here. And let's draw for now just one copy of dk. Oops, yeah, dk x there. Okay, so there's certainly cycles inside of this graph here, but there's no cycles of length 3, 4, or 5. I want to rule out cycles of length 3, 4, and 5. So if there were a cycle of length 3, 4, or 5, what could you tell me about it? It's not inside of this thing here, so it's got to use a vertex up here at least, right? So it uses a vertex up here. Now there's no edges inside of this, so if it uses an edge, a vertex here, it's got to use an edge going down to this thing here. Okay. But if there's a cycle using this vertex, it enters it and it's got to get out of it somehow. What do edges going out of this look like compared to the edge that I've drawn already? Can this does this vertex send another edge to this copy of dk? No, right? It has to send it to a different copy. Let's call this one dky. So it could send one there, okay? There's no edges between these things here, so it's got to get back over here somehow, right? This vertex and this vertex, to get back to each other, they have to travel back up again somehow. How can they do that? How can I can extend this path to get back up to R? It needs to get back up to R somehow. Can this vertex send an edge up to R? No, right? There's only a matching between this graph and R, or so I have to travel inside of this across an edge to get back up. Maybe I travel further, but let's just say the best I could ever hope for is definitely crossing an edge and then going back up here. And then what's the best I can hope for? For this to go back down here and then travel to there. That's the shortest cycle that I could ever get, where I have like zigzag. That's the only way to get up to R. I have to get up to R twice to have a cycle, maybe even more. What's the length of this cycle I just created for you, though? Right, this is an 8 cycle.
6.
Oh, so, yeah. What am I saying? Wait, wait a minute. Yeah. Oh, yeah. Yeah, Ethan, you're right. Yeah, it's a 6 cycle, which is fine. I'm not claiming there's no 6 cycles. We can have 6 cycles, right? And in fact, we also have 7 cycles. dkx contains 7 cycles because d3 literally was a 7 cycle and d2 is a 6 cycle. Okay, so we can't avoid a 6 cycle in this construction, but this doesn't create a 5, 4, 3 cycle, right? They're not present in these, and there's no way to make one by zigzagging. You can't get a 3 cycle. You immediately don't have a triangle for the same reason you didn't have a triangle in the Zhikov construction, essentially, because there's no edge between copies, and that each vertex here is adjacent to one up here. Okay, so what about the chromatic number? So chi of dk. What's that? Okay, so actually I'm going to show that the chromatic number is at least k. Why is it at most k? Same idea as in Zhikov's theorem. Each of these dk's can be colored with k-1 colors. Sorry, oh, I made a mistake here. Not a big mistake. These are dk-1s, right? Each of the copies below are dk-1s. I'm creating, this is d, the whole thing is dk. Okay, so actually let me fix this claim here. Let's just say equality, because that's what we'll actually prove. So that the chromatic number is at most k is easy. Use k-1 colors by induction on each of the dk-1s, and then introduce one new color for this super large independent set above. Same thing as in Zhikov's, no problem there. So the real question is, why does the chromatic number not remain dk-1? Okay, so suppose there exists a k-1 coloring of dk of this new graph here. Okay, so pigeonhole principle. What? We'll get there in a second. Let me think. Exists a set X of that many vertices with the same color. Oh, yeah, okay. So we got a k-1 coloring of dk. All the vertices up here have been colored somehow. They're independent, so in principle they can all get the same color, but they might not get the same color, right? In fact, if they all get the same color, there's no hope to finish the coloring, because then I'd only have K-2 colors available to me for these things above. So I should expect my colors up here to be mixed, okay? So Pigeonhole principle says there exists a set X, so a subset X in R of VK-1 vertices of the same color. Remember, R had size K-1, V K-1, D K-1 plus 1, right? So if I go back up to R here and look at all the vertices, there's this many vertices in R. If I try to, I don't have enough, I have too many vertices to avoid a set of this size, all of the same color. I've got K-1 colors, and I'm trying to avoid sets of this size in each color, but I've got one more vertex than I could get away with by keeping that. Okay. In fact, oh, I see. Yeah, you know what? In fact, I don't even need this many to get that. Right? Actually, how could I guarantee that? I could guarantee that. Yeah, okay. So the original thing I had was correct. Actually, even R of this size will give me that. K-1, V, D, K-1. That's a -1, -1, plus 1. That's the appropriate number for Pigeonhole. If each set is of this size, this many colors in it, but I have +1 at the end, there definitely exists one color class of that size above. Okay. But I mean, whatever, like I put this, that's bigger, so that guarantees it too. But actually this is, I only need that many vertices up top. Okay. So there's definitely a set of vertices above that are all of the same color. Okay. So this is this X, and everything in there is red. Every vertex gets red. Now, look at D K-1 X corresponding to this. There's a matching between these two here. So what does this tell you about the color red and D K-1 X? Can't use red, no red, right? No red vertex in there because all these guys are red up here, and they rule out red for all those. So that means that this is somehow colored. This has a K-2 coloring, right? Because I can't use red, and I've only got K-1 colors to use. So the remaining K-2 colors appear here somehow. But that's impossible because D K-1 requires K-1 colors by induction. Okay, this violates induction. Okay, which is a contradiction. And that's the end of the proof. Okay, so Pigeonhole gave us a set above that was too big. Not too big, but was as big as one of these DKs and guaranteed that it used up that color there. Notice though, you know, without that fact that these were all red, you don't get an immediate contradiction. Imagine I just grabbed an ordinary X here and there was some mix of colors here. And then I looked at the DK-1 corresponding to that X. This matching doesn't say you can't use red. It just says, oh, it's a little bit harder to color. Like this vertex can't get the color of that vertex. This vertex can't get the color of that vertex, and so on. That doesn't mean you can't color DK-1. Like maybe you could still color it under that assumption, right? Just because you lost one color at each vertex doesn't mean you're out of luck. You might be, but it doesn't guarantee it. But in this scenario, when they're all the same and you have this matching, then you lost a color here, and you can't lose it. You can't afford to lose a color because you need all K-1 colors in those copies. Okay, so that's it. These are 3 graphs from the Hall of Fame. I will show a far-reaching generalization of this, maybe even next lecture. I'm not sure if I'm doing this next time or when we get to a later section in the chapter, or later section in the book. But the fact is, this immediately says, okay, well, we were able to avoid 3, 4, 5 cycles. Can we avoid 3, 4, 5, 6, 20, 30, 40, 50, all the way up to 100 cycles and still have high chromatic number? And the answer is yes. And we'll see a proof of that at some point. Okay, good.